I have written a program that plays Connect 4. Let's see how I did it and if it can beat other Connect 4 bots. There's actually a bunch of fun factoids about Connect 4. Let's go through them real quick. Start with the one that Connect 4 was invented by David Bowie, which would have been cool, but it's not quite true. The game actually precedes the famous rock musician by a couple of centuries. Legend has it that Captain James Cook used to play this game during his long voyages, and he did go on some really long voyages. He enjoyed the game so much that the game was dubbed Captain's Mistress. It was rediscovered in the 20th century a few times, most prominently in the 70s in the US, where it became quite popular under the name Connect 4. And this is exactly the name the game is known by these days. By the way, I somewhat appreciate the fact that the name of the game is actually the game's rules. I mean, how convenient is that? Take notes, cows and bulls, domino, and tic-tac-toe. While it was all the rage in the States on the opposite side of the globe, although not so widespread, but the game existed too. There was a version published in the Soviet Union. It was published in one of the least Soviet of all Soviet republics, Estonia. The game wasn't called Connect 4, but Gravity Tips. And look, I even found a picture. Let us just spend a few seconds appreciating this artifact. I think it's a remarkable piece of design from the Soviet toy box covers industry. Just look at the board. Apparently, Comrade Jeffrey, pictured here, has no idea about how the game is supposed to be played. And this is what happens when you change the name from Connect 4 to something else. Continuing with the story of Connect 4. One of the more interesting things about it is that it is one of so-called solved games, meaning mathematicians have calculated all possible moves, all strategies and all possible positions, and there are officially no secrets to Connect 4 anymore. It actually was solved twice by two different guys just a couple of weeks apart, so you can imagine what the second guy felt. There are also scientific papers written about Connect 4 with all the results of all that scientific research. By the way, one of the things I found interesting in this paper is that they refer to the game pieces as men, as in put the man in this column to complete a 4-man group. And you should understand that the paper was written in 1988, so obviously in 2021 we should say person. Or maybe I should just call them checkers or discs. Finally, and this is probably my favorite part, original game box art, seen here, became a meme, which is a perfect ending to the history of this game. Now let's jump into breaking it with the power of Python. Let's define the goal here. There are a few websites out there where you can play Connect 4. I picked this one, c4arena.com, because A, it is not written in Flash, and B, it doesn't shove an ad in my face every few seconds. And actually C, it's not a perfect AI, which is important, and a bit more on that at the end of the video. For starters, let's benchmark me, a human, and my skills against AI of C4 Arena. It has a choice of 3 difficulty levels, easy, medium and hard, so let's see what my performance tallies up to. Well, at least I defeated the easy bot, although it's not by any means a glorious victory, 6-4. Oh well. Well, this one is definitely a step up. For AI, that is. I feel that if I wouldn't make silly mistakes every minute, I would end up with much better results, but we have what we have. That is, machine wiping the floor with me and hanging me out to dry. Finally, the hard bot. actually seem to gather some more wits for this one, as there are clearly fewer stupid mistakes, but it didn't help much. I managed to squeeze one victory and a couple of draws, but other than that, the floor is wiped again. But at least now the goal is quite clear. Write a program that would avenge me and kick Hard's AI's shiny metal butt. So let's jump right into it. I mean, the program. Alright, image recognition is pretty straightforward, just find the grid and test the color. Now, to the playing algorithm itself. If you look inside the program, and you actually can, because the link to the source code is in the description, you'll see the following parts: naive part, minimax part, and heuristic part. Let's look at them one by one. Naive part is not too far from how I play as a human, namely follow these two rules. 1. If you can place a disc and win, do it. 2. If your opponent can place a disc and win, block them by placing the disc there yourself. This is it. For our first test, let's also add the logic that if there are no naive moves, we just use a random generator to pick a column and see how far it will take us. Let's start with the easy bot. Not too bad actually. It's a little discouraging for me as a human when a random generator plays a bit better than myself, but okay, overall good start. Let's see what it will do against the medium bot. And obviously a strategy of throwing the discs randomly fails against the first serious opponent. It managed to get one draw, but this is some weird luck, no doubt. Anyway, let's get to the next step. Next step is actually the heart of the whole program. It's something that is called a Minimax algorithm. And to understand how it works, let's look at how an algorithm can play any turn-based two-player game. It doesn't have to be Connect 4, it can be chess, checkers, or tic-tac-toe. Players make their moves one after another. By the way, in the literature they don't use the term turn because it may be quite ambiguous. Instead, they use the word ply, as in plywood. So ply is one move of one player. So back to the game, how can we find the best move in any situation? We can do it by making a tree, where each node is a position on the board and each branch is a possible move. It's quite easy for Connect 4, there are no more than 7 possible moves in any situation. Let's say we have built such a tree for a few plies, with all the possible moves. This is what a piece of such tree may look like. Some of the branches end up with W for win and some with L for lose. Now, what do we do with all these? Let's assume two obvious things. Whenever it is my turn, I will always choose win over draw or draw over lose. Your opponent also wants to win, so when it's their turn, they will choose whatever is the best option for them. So when we start to traverse the tree, leaves to root, we should pick best options for all odd layers, that is for ourselves, and worst options for even layers, because they're also the best options for the opponent. So it goes best, worst, best, worst, best, worst, or in other words, maximum possible score, minimum possible score, maximum, minimum, maximum, minimum. Now you probably can see where the name of this algorithm, Minimax, comes from. Note that in our case we have a rather simple setup where all the options to choose are from win, draw or lose. In other games what you can do is to assign some sort of scores to different positions with many factors and variables included. So clearly what you would do is to pick maximum score for yourself and your opponent will choose maximum for them, which is minimum for you. So again, you have maximum, minimum, minimax. Minimax is a powerful algorithm, and it's exactly what most turn-based programs are based on. So take, for example, computers playing chess. If you're old enough, you may remember, and I actually do remember, there was a computer defeating then world champion Garry Kasparov, who, by the way, is my favorite chess champion of all times. So the name of that computer was Deep Blue, and it was using a version of Minimax to choose its moves. Anyway, we can set up a depth up to which our algorithm will explore future positions, but beware, each ply is adding 7 times more positions to analyze, so it quickly becomes rather unwieldy. Let's look at the numbers together. If you want to look 1 ply ahead, that's 7 positions to analyze. 3 plies, about 400 positions. 5 plies, just under 20,000. 8 plies, over 6 million. And 8 plies is not that far ahead actually, it's 4 moves by each side, that's it. And this is where I introduce another little improvement. Something that is called Alpha Beta Pruninng. Again, the proper version is a bit more complex, but in my simplified case, it goes like this. If I start checking the moves from one particular position and I found out that move leads to my victory. In this case, I don't have to check other columns. I'm not going to pick anything worse than victory anyway. Alternatively, if on the minimal level I discover that opponent wins, I pick that as a final result, because whatever other options are, the reasonable opponent will always choose to defeat me if they have a chance. I will note it again, my version is kind of a kiddie version of Alpha Beta Pruninng. In real life it's a bit more complex, but the general idea is the same. As for the time saved, in my case it was quite successful. It sped up the calculation by more than 10 times. Alright, with Minimax and Alpha Beta implemented, let's see how it will play against the C4 Arenas bot. I want to note here, I still wanted to have some reasonable time the bot spent on one move, say less than a second. I don't have all day waiting for it to go too deep. So what I ended up with is a program that analyzes the game 6 plies deep. In this case, it takes about 0.3 seconds to come up with a solution. Now, if we increase it to 7 plies, it will take between 1 and 2 seconds, and I would say that's a bit too long. Anyway, medium level bot. Well, it did manage to score a couple of well-deserved points, but overall not as good as expected, is it? I would say it's marginally better than I was. So let's look into what went wrong here. So this simplified version of Minimax only works if there is a way to victory or defeat in the upcoming few moves. Our Minimax only goes 6 plies deep, meaning if there is no clear path to victory or defeat within 6 plies, Minimax will come back with all zeros. In this case, my bot will just pick a random column to play, which is kind of what the first version would do. Questionable idea, especially during the initial phase of the game. It almost literally throws spaghetti at the wall, and by the time something sticks, the bot can find that those spaghetti spell disaster. So how can we fix it? Well, one way to go would be to try to get to deeper levels of Minimax, whatever the costs. Options included waiting for hours for my program to make a single move, purchase a new, more powerful computer, or maybe a server farm, learn a language that is faster than Python. I heard some good things about C++. I didn't really like any of these options, so I decided to try something else. Basically, I came up with a little heuristic.
Heuristic.
heuristic solution. Heuristic is a fancy word for there's no strict math behind it, but it seems like a good idea, so it's probably gonna work. Here's the plan. We can assign a score to every position based on how many potential incomplete 4s are there. Some points for 2s that can become 4, and some points for 3s that can become 4. Now what we do is we put a disk into each column and calculate scores for that position. At the same time, let's try putting the opponent's piece into each column and also calculate their score. So whichever column gives me the best score while giving the opponent the worst score is the column to go. And final touch, if the program still cannot arrive at the conclusion, pick whatever column is closer to the center. And on top of this, as you remember, we have Minimax. So if after all these heuristic manipulations we come at least 6 plies next to the victory, the program will beeline straight there. And if there is a losing move within those 6 plies, it will steer clear of it. Alright, let's see how our program plays with this new improvement. And let's go directly to the boss fight, the hard bot. Well, with only 1 draw and 9 victories, finally we have our deserved revenge over the hard bot. Which means this is the end of the video. But before I sign off, I have a couple of see also items. First, the bot that I have built is obviously not the perfect bot that can play Connect 4. And since Connect 4 is, as I mentioned before, a solved game, there are so-called perfect bots that can calculate all the possible moves up until very end of the game, and they know for sure, without guessing, which move ends up with which result in how many moves. They can also be written in languages that are orders of magnitude faster than Python, which is kind of crucial when you have millions of game positions to go through. And here is a perfect bot that does all that. The solver at connect4.gamesolver.org, the link in the description, from a guy named Pascal Ponce. Moreover, this site has a popularly written tutorial about how to write a perfect solver like that yourself. It starts with some simple Minimax and Alpha Beta Pruninng, same as I did, but it goes much farther and achieves much more spectacular results. So I highly recommend this site if you're interested in how to build a Connect 4 bot the right way. And finally, Code Bullet, a channel that kind of inspired me to start writing programs in the first place. Recently, he also had a video about Connect 4. As always, quite entertaining, so give it a watch too. And this is it for this video. Like if you enjoyed it, subscribe for more game-breaking Python programming. Source code is in the description, and I will leave you with some more of Connect 4 action. Hope to see you in the next video. Bye.